probably. All right, let's just see if it goes.
So it's
I'm recording right now. We'll
okay.
see.
All right. Okay. So today we're going to start thinking about how to program parallel computers. So I think, and go out there and tell me if you don't think this is true also, that if you do find a course on parallel programming, what you're going to find is basically an approach which says, write more threads. Break your code into more threads. And look at diagrams like this, think about mutual exclusion, spin locks, and so forth. Okay. And one of my colleagues across the street has explained, as I've alluded to in this class, there's a lot of problems with that. What we do in this course is we take a very different approach. So a software architecture, and this is not, if you pick up, standard book on software engineering, this is not their definition of software architecture, this is mine. So I'm going to maybe call this a pattern-oriented software architecture. It is a hierarchical composition of structural and computational patterns. These are the these are the computational patterns, these are the structural patterns, right? So we've already seen a few examples of how those are used hierarchically and in composition. Okay? Now, question to the class is, we've talked about our super programmer skills. What super programmer skills do computational pattern sophists develop? What super programmer skills do structural patterns help us develop?
It's on there. It's in the picture.
It's in the picture.
So,
Well, that's the kind of thing I get to say, but that's, that's not the thing the students get to say, right? So tell me more about that, how it's all in the picture. Yeah. Oh, go ahead, George.
no, here.
I don't mind.
Oh, yeah.
Up, man.
Okay, so structural patterns are more like generally mathematical approach, I believe. And computational patterns, I'm sorry.
Right.
And the structural patterns are more like a software design approach. Where
Right. So our three skills of super programmers are
code 10 times more code.
10x, produce 10x more code, the code runs 10x faster, they have 1/10 or actually 1/100th as many bugs. Right? So look at these patterns as classes and tell me how does that line up with so Johnny, now that I know who you are, I'm going to start picking on you. So super programmer skills, how do these help?
Better analysis, better algorithm.
So, okay, yeah, that'll buy you some time in like a doctoral qualifying exam. That's not an answer. I've forgotten your name.
Jonas.
Jonas? Yeah.
Better computational pattern knowledge allows you to write more if you can do more stuff, and better structural patterns allows you to organize what you're doing better.
So
you can make it
organizing,
faster.
so efficiency, correctness, productivity. Nothing you said was wrong, but, and I mean, sometimes I worry I'm too repetitive in this stuff when the class is not, I mean, and I think if you get it, it's not like I've got this weird right answer and if you get what these things do for you, then you'll immediately see how it ends up. Metallark?
Is it transitivity?
Transitivity.
Meaning you have a pattern that you recognize, hopefully at a finer grain, you can recognize that you can use it in multiple cases.
So if you recognize a pattern, you can recognize you can use it in multiple cases. That is absolutely true, and that is related to reuse. And reuse is our biggest tool in our toolkit for productivity. Okay, so that's one relationship. Jim?
It seems like the computational patterns would help you with the speed and the less bugs, and the structural would help you with the productivity and less bugs.
Sounds pretty right. So the computational patterns have to do with speed and less bugs. The structural patterns have to do with modularity, correctness, maintainability, and less bugs. And these two together help you with productivity. Adam?
Yeah, I think it's also important to note how it helps like teams work as opposed to just like one programmer.
Right.
Because if you look at like a traditional design pattern book like Gang of Four or something like that, the advantage is that it gives like programmers like a common vocabulary to solve problems with. So like if someone's like, oh, that I'm using the observer pattern to do this, like you'll immediately kind of know how their code's working. So this kind of gives you that same shared vocabulary for parallel programming.
Yep, absolutely. So just to repeat that Adam points out a great point about patterns, which is they give names to things. Then we can organize what we know about patterns around that name, and then we can communicate just in a single word or a phrase a lot about it. You know? And I'll, in the interest of time, I'll save the war stories for later, but I'll talk about exactly the point Adam brought up later in the lecture. John, yeah.
So, I'm guessing that clarity would be more classified under a structural pattern. But what happens when you lose clarity for the sake of efficiency?
Great question. What happens, so these structural patterns help you get efficiency. What about, these structural patterns help you get clarity. What about in the interest of efficiency when you begin to blur things? My answer is that's your last resort. And no, and there's a deep reason for that, which is, and it goes back to, you know, why we're not programming this way. Right? No, I mean, a lot of excellent programmers sit down and program this way, and they do speed up code, oftentimes. But they're almost always, you know, winning the battle and losing the war, if you know what I mean. And the reason is that in the absence of some sort of clarity about the structure, it's very hard to test your code in isolation. It's very hard, and because it's hard to test it, then it's hard to optimize, because you know, because I'll show you results at the end of class, that you only get to the leading edge when you're really just barely sure that it's right. And so you better really have a testing structure that tells you it's right. And if you start blurring, and we'll just pick this Python filter, you start blurring these two filters, it starts to get pretty hard to make sure you're right. Whereas you've probably got some sort of test environment for this filter and a test environment for that filter. And as long as that's really working, you can have confidence. Oh, boy, that's really a little risky what I did. Oh, regression test ran last night, looks like it's got a pretty clean bill of health. Okay? So that's a really excellent point, and that's an advanced concept probably we won't get till later in the semester about all this gets, everything I'm going to describe today gets you to the point of really producing high performance code. That last factors of 2, 4, and so forth require a whole other class of optimizations. You want to get that out of your code. Then, you know, you're kind of going off the track of just good, what I may begin circling structured parallel programming. Okay, but first let's get the big wins, you know, the factors of 10s of the parallels in our machine, and that's what I'm going to talk about in this lecture. Okay, so this is, I'll keep flashing it, the way we architect parallel software. We identify structure, look at the key computations, look at the structures that support those computations, look at the computations that go in those structures back and forth, you know, the layout of the factory, the machinery, and how it all hangs together. And this is an iterative process. And we do this in this course in a very particular way. We have what's called a pattern language. And what that has, what I've shown you so far, is what's at the very top of that, which are the structural patterns and the computational patterns. And today we're going to begin, talking about the parallel algorithm structure patterns. So this is just the general layer cake of this pattern language that Tim Matz and I, as well as grad students, put together. It's got structural patterns, computational patterns on the top. This is how your general strategy for how you parallelize. We'll be spending a lecture on this. This is how you implement it in software. This is how you execute it on hardware. Okay? These are the real patterns. No more, no less. It's a lot to look at all at once in the beginning. But you're already familiar with these. Today we're going to become familiar with these, and over the course we'll get through this whole language. Let's focus just on this for now. Okay, what do these parallel algorithm strategy patterns do? They're just what they say. There are parallel algorithm strategy. general strategy. It's just a very general approach. Generally, how am I going to parallelize the software? There they are again. There they are in context. Now, this is getting back to the issues exactly that Adam brought up. What do patterns generally do for us? They give us a name, so we can communicate better. That may sound like something small, but if you don't have a name, say, for geometric decomposition, if everybody in your group, everybody in your company doesn't know what that is, you spend a lot of time at the whiteboard. Oh, well, no, I call that something else. Are we talking about? And then they draw a diagram. You go, yeah, that's what. Okay. And then you have a lot of conversations like this. You read that in a documentation of software says we use the geometric decomposition pattern. Don't know what it is? It's like, well, thanks for sharing that. You know exactly what it is. Boy, that helps a lot. Now I know what they're doing. Or now I know at least what they think they're doing. Maybe they didn't do it right, but at least I know what was in their mind when they did it. Okay, so those are names, categories. What you're seeing in the Gang of Four book on design patterns, object-oriented programming is there's a lot of shared, once we call something like geometric decomposition, in our case, or something like the abstract factory pattern, in their case, then you can begin to gather information. These are the experiences we've had for it. These are some examples of what it's good for. You try to implement that, here are the problems you're always going to have. Right? So you begin to categorize all that information. Makes sense? Now, in particular here, we make a stronger statement than they do in the Gang of Four book. Not at all. They say these are really nice things to do object-oriented programming. We say this is all the patterns you ever need to worry about if you want to parallelize software. Okay, so that does two things. It's necessary because, well, look, if there's 7, you don't really have an excuse not to consider them all. If it was 225, and you go, well, okay, I stopped at 171, I'm sorry. That's all I had time. 7 patterns you ought to, but we claim it's also sufficient, which is, in this course, if you think of how to parallelize something, and if you think of all these 7 ways, and you finally go, I think among these, geometric decomposition, for example, is best, then you're done. That's enough. You don't have to go, well, I wonder if I took a course at University of Illinois, would I learn other very different ways of parallelizing things? Maybe Stanford, gosh, I want, we claim this is it. Okay? So there's a lot of power there. Right? And you're welcome at any time. You think, when they come forward and say, no, how would you possibly parallelize this, with these patterns? We're happy to talk. So top down, these are the things you think about. And I'll repeat again, and I'm sorry if it gets repetitive. This whole process of design is an artistic exercise. Okay? Now, so far, I would say we're at the era of software engineering where it's a totally artistic exercise. I mean, let's face it, people do whatever the heck they want. They're, even in the most restrictive companies, there are very modest standards, at least anywhere I've seen, about how you code. After that, you're on your own. You can make up your own names for different software approaches. You can basically do whatever you want. So relative to that total chaos, we're just trying to raise it to an art. Maybe another 20 years it'll be a science, right? Right now we just like to make it an art, like civil architecture is an art. We'd like to be able to create blueprints that people can really read. And here's part of the art. You look at the data you're working on, and you go, well, where is it shared, and how do I access it? Or you might look at the tasks and say, what are the tasks? How do they group together? Is there a particular order between them? And then, while you're doing these, you're going to go, well, what software structural patterns might best support that? Or maybe, this is really all just dense linear algebra. I mean, that's all that's really happening here. Okay, I just need to put a little structure on that. Okay, you get some sense? Okay, so from those top level tasks, this is Tim Mattson's view. This is his old pages in his old book. And we'll show readings in the new PDF. He's been kind enough basically to give you all an advanced edition of his next generation of this book. This is how he suggests you kind of make your way into these different patterns. Okay, so these particular patterns are called the parallel algorithm strategies. Okay, so if you're really, it's all about the data, then you might look at pipeline, discrete event. If you, sorry, the flow of the data is pipeline or discrete event. So the point is this data is streaming through. If it's about the data sitting more kind of statically organized, say large matrices, 2D, 4, 3, 4-dimensional matrices, then if it's linear, then that naturally lends itself to data parallelism, or a pattern you'll learn later called geometric decomposition. If it's kind of recursive, you might use divide and conquer. Similarly, if it's all in the tasks, you might use divide and conquer. Or if it's more linear in structure, and I'll show you what I mean by that, you might use task parallelism or speculation. So I don't expect you to, like, oh, okay, now I can just go out and parallelize arbitrary software. This is the first time you've seen this. This is your introduction. You're going to see this a lot during the class. Okay, so what I want to do is march through 3 of these particular strategies for parallelism today. I'm going to start with task parallelism. So this is a kind of, those of you who are familiar with the book design patterns know this basic structure of describing pattern. When you use this, when the problem manually decomposes into a distinct collection of tasks. What's the solution? Define the tasks and a way to detect when the computation is done. What are some of the gotchas? Well, you need to manage or remove dependencies so that the correct answer is produced regardless of the details of how the tasks execute. Okay, so that's the big challenge in task parallelism. And if we push that all the way down the threads, that's where we get into all these synchronization issues. But we're going to try and manage that at a higher level than just getting thread by thread. Okay, oh, I think I know how I can do that. So this is about correctness. Schedule the task for execution in a way that keeps the work balance between the processing elements of the parallel computer. Oh, sorry, I didn't notice that. What's this? And that's about efficiency. So we need to make sure we've got all the synchronization in place to get it correct. And then we need to think of these tasks or associated processors. We need to keep all the processors busy. So this is called load balancing. You need to kind of balance the load so that we're getting good utilization out of processors. So the extreme case of this is the embarrassing parallel pattern where we have no dependencies. So in embarrassing parallel, tasks are independent. So the parallelism is so easy to exploit, it's embarrassing. Okay, so George, what's an example of this you've seen just recently?
The Ericsson routers and switches.
Yeah, Ericsson network processing. I showed you that in the slide. We were actually using the Tylera 64 processor chip as an example of a network processor where, because all the channels in a router are entirely independent, processing them as embarrassingly parallel. Okay. Now, the next thing is separable dependencies where it's not embarrassingly parallel because there are some dependencies, but we can actually duplicate the data in such a way that once we duplicate the data, then the computations can all act as though they're entirely independent. Okay? And these, we actually won't show any examples of this today, but we'll be seeing them as the course goes along. And then functional decomposition is where basically you fail the first 2 cases and you really need to get into the details of practically how these things relate. But we want to be looking at high-level function, not immediately going down to details of mutual exclusion and so forth. Okay, so here's one way of looking at the game engine. We'll be talking about, through the course, we're revisiting this, at other ways we might structure this game engine. Okay, so just very broadly, here's the core of the simulation data state. Then we've got some media that we're interacting with. Here's the primary input from the game player. There's some audio data state. There's how you render it. There's some animation smarts in there. There's a front end and so forth. And then here's kind of the core of this. So this is what has to really run fast, and this is what produces the character game. So in there, as in our simple game, we have a little bit of physics, we have some collision detection, we have some AI, and some particle systems. Now, this is the high-level architecture of this game. This is really it. Now, how that executes is these each get decomposed into a pool of tasks. That is, they create little units of work that need to get done with a certain priority, and then these tasks are then put into a pool, as we'll see lower levels of pattern language, and then based on how the dependencies met and the task priority, and then we're trying to, we have sparse and scarce resources on our actual Perl processor, and so basically the challenge then is how to schedule these based on their priorities and utilizing our hardware so that our bus utilization, our load balancing, and concurrency for correctness all get satisfied. Okay? So again, this is, you know, in civil architecture, you know, this is where I kind of take you out and I show you, you know, this is what a ranch house looks like. This is why people build ranch houses, you know. Not a lot of stairs to go up and down, and spread out, very low-cost construction, you know, presumes it's easier to go, you know, sideways than up, when exactly would work in downtown Manhattan, you know, but this is, so this is all I'm trying to, you know, we'll be seeing some examples, but this just generally getting some idea of what kind of parallelism this task parallelism offers us. Okay, let's look at that in contrast to data parallelism. So this we use when your problem is defined in terms of collections of data. So remember, as we went through that chart, this is a data center. Okay, so this is when it's immediately obvious that the action is all in your data, say all in your matrices and so forth. Okay, so, and it's operated on by similar, if not identical, and we'll, later in the lecture we'll get to exactly how similar does it need to be and why it doesn't exactly have to be identical sequence of instructions. So concurrency of data. So we define collections of data elements that can be updated in parallel, and then define the computation as a sequence of collective operations applied to each data element. So we have kind of, we're operating many tasks, but the nature of what's done in that task is defined in one place. So what I mean? So, you know, this is single instruction data, single instruction multi-data, or single program multi-data applied to independent data sets.
Like,
All right.
like, like the homework, right?
I'm sorry?
Like matrix multiplication.
Yeah, so our matrix is decomposable, although there is some sharing. Different elements are reused in different ways, right? But, yeah. We'll see even more data parallel examples. So, here are, you know, kind of types of operations which immediately identified as data parallel. So we have element-wise operations. So we're taking these two independent. So these are all independent, and we sum them and collect them. There's nested parallelism. So this is kind of interesting. Certainly, if you have a dense matrix, it's the kind of inherent data parallelism there is clear. We can have a tree structure, right? And that at the leaves of the tree, that's also independent data, right? Or that can be linearized. So we can take this tree structure and we can flatten it out and just look at the leaves this way. Okay? All right, then oftentimes we'll see once we do something like this, then we have to reduce it all down to one value, like a maximum or something, or sum of all. This could be a plus, or this could be a max operator. And then alternatively, we can essentially be doing data shuffling, which is still a kind of data parallelism. You notice that shuffling this around, and I may mean literally shuffling as in a perfect shuffle or M shuffle or so forth. Shuffling this item doesn't affect in any way shuffling that item. So again, this is just alone. So now we're talking about another kind of architecture, and I'm just talking about different, and by now just civil architecture, I'm just talking about different elements and different things that help you recognize. Is that Eric Rogers?
Yeah.
Yeah.
I'm curious, let's say you needed the sum of all those things, and you wanted the min, and you wanted the max of the same data.
Mm-hmm.
Does that, you still use this model, and then you just create like a new
So Eric
operator?
asks, well, what if I want the sum, and I want the min, I want the max, and what the heck, you know, let's take the difference, and the maximal, you know,
Yeah.
anything. Sure. That's all data parallel.
So you
In fact,
create a new operator, and then you just use this one?
I just need a little more local storage, right, to keep all, but I can compute all those in a series of cycles as I go. That's still data parallel. Good. Good to, start thinking, when would I use that? How would it work this way? Okay. Rishi?
Yeah.
Yeah.
So if you wanted to compute like all those functions, would you store an array and then compute them, or would you just have like the parallel architecture keep on doing the computation, just like like taking the information, collecting it all, and then doing it independently?
Okay. If I understand your question, the question is, would you store an array and then operate, or would you collect a little bit at a time? Is that basically the two distinctions you're making? Well, in some sense, it doesn't matter what you're asking. The answer is the same, which is it all depends. Okay, and we'll see a lot of the art of getting speed out of data parallelism is how you collect the data. And so Katja and David here are two good examples. In Katja, for her to get parallelism out of her speech recognition stuff and her audio processing, a lot of her time is figuring out how to coalesce the data to get it all set in the right place so you can do all these operations. For David, for the kind of stuff he's working on, it's much more natively data parallel. But just because it doesn't, and that's maybe an advanced nuance, but just because it doesn't leap out to you, this is data parallel, because the data is spread out all over, say in a big graph or in some other data structure. The question is, are these basically relatively independent, and can I coalesce the data so that I can operate it all at once and then put it back? A little bit general, we'll be talking about some real examples. But it's good. Would I do it this way? Would I do it that way? All right. Serial matrix multiplication. I think you're all becoming very familiar with this one, right? We can operate on a whole row and a whole column simultaneously. Sorry, whole column and a whole row simultaneously. Okay, or this is one that Tim Madsen liked. This is the cellular automata, the game of life, something like that. Things where you do a lot of little local computations and update locally. That's also a good example of data parallelism. Okay, last general parallelogram strategy I want to show you today is pipeline. So this is when your problem can be described as data flowing through a sequence of computational stages. Where flowing here is going to be pretty important. So you define a set of stages set up with data flow connections between them. You set up input-output channels to support data-driven execution. And then parallelism comes from multiple stages acting at one time. Okay, so here's a couple small graphical variants. We could just have going from one pipeline stage to another, or we could have some branching and coming back together. But the key thing here is that the flowing, and moreover, there's kind of the aspect of pipeline parallelism is that these things can all be going simultaneously. Okay? If this pipeline stage is entirely dependent on, has to sit and wait for operands from this one, then that's not pipeline parallelism, because we'd only have one pipeline stage. We'd have something kind of just flowing through here one at a time, and then it gets to and then we can flow through again. All right? Okay. So this is just a graphical example of this. Sorry, I forgot what I was looking at. So this is just, we have a stage 1, stage 2, and stage 3 parallelism. Okay? And this is a real example from some seismic data processing where Tim spent a lot of time. You load the data, you process the data, you save data. And what makes this pipeline is you have a lot of data to load, and you can just keep loading it. You have a lot of data to process, you just keep processing. You have a lot of data to save. And just as we saw in a single pipeline architecture of a processor, which is a particular kind of pipeline parallelism, it's important that these be balanced, otherwise one of these becomes the whole latency bottleneck. Right? That will be true in this kind of parallelism also. Okay, so this is your first reading assignment, but Tim has been good enough to give you a copy of his book, upcoming to be released, and so we should probably break it down and actually start to read it. So let's get a look at these particular patterns. Okay, now how do we apply that to software? Okay, so let's look at our structural patterns, and what I'm going to show you today is ways in which your choice of structural pattern naturally causes you to tend to particular types of ways of parallelizing it, right? Now, I want to be clear is when you're thinking at the high level architecture, you don't have to, and as a matter of fact, Tim and I differ on this a little bit. I think you should not be thinking about parallelizing at all. Tim, after 30 years of parallelizing parallel programming, says that's impossible. I'm always thinking about how to parallelize. There's never, but I actually think, conceptually at least, you should be able to architect a system in such a way that you don't know, you have a good high-level architecture and you don't know whether it's going to sequential software or it's going to sequential hardware, parallel hardware, or even pure hardware, that is to say, a circuit. When I think back of large-scale descriptions of systems, industrial systems, I think, well, you could have used the pattern language to describe those at the top level and then build an application-specific integrated circuit out of it. That's how independent it is. But at the same time, the nuance of today is, although that's true, we will see that certain structural patterns naturally tend towards different types of parallelism. So these are our patterns, okay? We've seen these before, and we've seen these three, and so I'm going to use these three to demonstrate today how we can go from these structures into particular types of parallelism. Okay, so here's pipe and filter, right? Just make sure, all right. I'll first ask you, what were some of our examples of pipe and filter? Somebody nailed it last time. Oh, go ahead.
MapReduce, right?
MapReduce is another structural pattern. Okay. Is it Jason?
Yeah.
Jason? What?
Image processing, is that a type of
Image processing was a pipe and filter. What's the one you use every day? That's pipe and filter.
Unix pipes.
Unix pipes. No, we did a lot of, or then I think someone said, oh, well, this filter, the DSP filter or something like that. And it's like, well, the poster child of pipe and filter is, George?
Spam filters? No?
Spam filter? No, that's the kind of pattern match on filter. Somebody got it right last time. Compilers, right? Compiler was our, okay. All right. Okay, so what kind of parallel are, I have to say, I sit there as I do these sets and go, oh, well, they get really tired of me asking the same questions. Apparently not. Apparently doesn't really hurt to go over it maybe one more time. Okay, so what kind of parallel algorithm strategy would I use? I mean, you don't know anything, this is the kind of thing that'll make you look like a genius at your next job, right? I mean, you walk in the room, you see a diagram like this, everybody's scratching their head going, God, how do we parallelize this? You don't even know what the words inside here mean, but you tell them what parallel algorithm strategy? Jonah.
Jonas?
Jason, Jonas.
Yeah.
Jason, Jonas, okay.
Like pipeline parallelism or data. You can just have
Pipeline
the data.
parallelism, all right. Yeah, see, he had the courage. All of you were thinking pipeline parallelism, but, right? But he had the courage to actually say. Absolutely. Just as almost every program has a pipe and filter structure at the top level of the architecture, almost every streaming parallel program will have a pipeline parallelism at the top level. So the notion of streaming here is we've got to get the streaming data through there. Okay, in contrast to what? I'll show you in a moment. But signal processing algorithms are full of this kind of thing. You just have data streaming through, or image processing. You just have endless data, video processing, endless data streaming through here. And because there's always endless stream of things, all these stages can operate simultaneously. Yes, sir. I'm afraid I don't remember your name.
Max.
Max?
Yes, so is this, just for clarification, sort of the software analog to like pipeline on the CPU?
pipeline.
Is this a software analog to pipeline on CPU? Yeah, I mean, we're right at the software hardware interface because this conceptual pipelining we're doing at the high level turns into actual hardware pipelining at the low level. And of course, at the lowest level, each instruction of execution is pipelined. Yep. Okay, how did that go? Everybody pretty impressed with Jonas? Yeah. Okay. So now, pipeline parallelism is really just a particular kind of what other kind of parallelism strategy? Eric.
I think it relates to the fact that the data becomes, I'm thinking of data coming out like
Did I
stage 2.
poker tell that I didn't like your answer? I noticed you stopped halfway. All right, slow down. Yeah. I gotta improve that.
Because the pipes are data, so the data's going 2 places.
Well,
That's
so
I'm
what is true is they only see their inputs and produce outputs, and there's no global or shared state. So in some sense, there has to be parallel data in there somewhere. So in that regard, I can kind of, I can understand what you mean, and I reflected on that as well. But in another sense, as we start to develop our kind of aesthetic for types of parallelism, I think we'll see, well, this is really very related to another kind of parallelism strategy, which is, Jonas, I'm going to start answering you when we just need boldness right now. So here's the hint, right? You've only seen 2, right? Eric thought it was data parallelism, so it could be task parallelism. It's got it. Okay, it's for task parallelism. So pipeline parallelism is really just another type of task parallelism, right? I mean, these tasks executing in parallel and the data is streaming through there. I mean, you can actually kind of, if there weren't so much feedback and so forth around here, we would call this pipeline parallelism. Now, this tends to throw people like, gosh, I just thought I was getting something and now I don't really understand what's the difference between pipeline parallelism and task parallelism. And, 10 years into the process or something, I finally found an analogy, every pipe wrench is a crescent wrench, right? But not every crescent wrench is a pipe wrench. There's types of task parallelism, many types of task parallelism, which are not pipeline parallelism. But there's a particular kind of task parallelism that's called pipeline parallelism, right? So pipeline parallelism is the pipe wrench, task parallelism is the crescent wrench, very general tool. Probably the most general tool in your toolbox of parallelism. Okay, iterator pattern. Okay, so remember this, we have an initialization condition, we do a bunch of stuff, that all has to kind of come together to create a barrier conceptually or in fact, and then we exit condition. And if we met the condition, fine, we're done, otherwise we keep iterating. Okay? So let me ask first, what are some examples of this? All right.
I remember mathematical convergence, which is probably a better way to.
Mathematical convergence
like a
for
calculation.
Image processor.
Max?
Yeah, it was, I think, probably the same idea at the same time, but like fixed point calculation.
Fixed point calculation, you're trying to converge towards a fixed point here, Metallark, did you?
All the recursive algorithms.
Recursive, well, this is not really recursion unless you turn tail recursion into some linear iterative process, right? Which you can often do, but this is not, we have a whole other pattern associated with recursive parallelism, right? So this is not, yeah, Jonas?
Gradient descent.
Gradient, optimization. Optimization is, so as we march through this, you are going to need to kind of internalize the high-level structural patterns and the computational patterns. Otherwise, as we keep going, if you don't have an intuition about those, then we're just going to keep layering on one thing that you don't understand on top of another. Which David and Kutch reminds me, I guess we need to have some homework assignments on this stuff so that people, I mean, I know it takes some sort of integration. It's hard to forward.
Yeah.
Knapsack algorithm using.
Well, knapsack is NP complete problem, so you can't just iterate, there's no for n, we know, but we'll get you through, unless it's a very big number, but we'll get you through, right? Yeah.
Machine learning algorithms? Like
So many machine learning algorithms have optimization, some sort of quadratic optimization at their core, and that quadratic optimization is of this form. Right. Okay? So that's the class of problem. I mean, all of you have done this, right? In your linear algebra class, you start out with something and you do things until, some exit condition, then at night, you just keep going around, right? While loops. David?
Kurt, you loved to use the compiler thing before, but this is to me the classic data flow. Any kind of data flow algorithm that you're iterating to a fixed point.
Data flow algorithm, this is a data flow in which you're iterating to a fixed point, yeah.
Yeah.
Yeah. So I think fixed point was mentioned, optimization was mentioned. Those of you who gave those answers, great. Those of you who didn't, start to try to internalize. Okay, but now, once we've got some sense of the type of computation independent of how we're implementing, how do we tend to parallelize this? What's the natural way to parallelize this? George?
Identify where we have like barriers, and where we have to share data and split the functions performed, that do not need to share data.
Yeah, so what George says, let's work backwards from that barrier. This is actually a very sensible way to proceed. We know, well, this is gonna have, we're gonna have to sequentialize right here. It's just yes or no, right? So everything's gotta be sequentialized. So we work back from there and we basically go all the way back to the beginning to this, okay, look at the data, look at the tasks, and what you're saying is exactly right about what we do inside this. How about just this general structure? How's the structure? You see this, okay, so you see this on a whiteboard, and you're rapidly becoming the star of the company, and and they're saying, oh, what are you guys doing? Oh, we're trying to parallelize this. You immediately go, what? What do you say? Or what do you tell them?
Maybe map reduce.
Maybe map reduce?
Because you would have to, the only thing you can parallelize is what's in the block.
That's the answer. So it's a trick question. What Dara said is the only thing that you can parallelize is what's inside the block, right? This is natively sequential. I mean, you have a barrier here, you ask a yes or no question, how much parallelism there, and then you go back and you start over, right? So what you do when you see people, we're trying to figure out how to parallelize, is go, hey, you gotta focus on the block. What's inside the block? I figured that out. Boy, we're struggling. There's got to be some parallelism here somewhere, right? Okay, does that make sense? Good. Okay. All right. So where is the parallelism in there? So this is correct. This is a real architecture. We have this pipe and filter. So in this kind of simple pipe and filter, do we have some parallelism? Supposed to be. What do you think? Do we have some parallelism? Adam, tell me where the parallelism is.
Well, yeah, for each actual iteration that you need to calculate, there's within that, there's stuff that can be done independently. So you can have like a pipeline stage where you have multiple instances of each pipeline stage running in parallel. So it's yeah, so that's it.
So Adam's saying is, yeah, I mean, there are multiple, this is all asynchronous, right? And so we should be able to operate on this in pipeline. And my response is, not necessarily, right? As a matter of fact, in the examples for red machine quadratic optimization we have going on in here, these are actually two distinct stages, and we have to finish this one before we can do this one. So this is my example of where a pipe and filter may lend itself to pipeline parallelism or not. Because remember, once we start this initialization condition, it's kind of like go, and then but we don't take any more data. We don't draw any more data until we're all the way down to the exit condition met. It's just all cooking inside here, right? So where is some potential for parallelism inside here? Well, I know it's hard to answer abstractly, but if we looked at this, what's this pattern? What's this, what pattern is this the little logo of? Things spread out, computations are done friendly, they come back together. Map produce, right? So that's it. So this is true life, as we're training the classifier for a support vector machine. Jason mentioned machine learning. This is kind of the core of machine learning. We update some optimality conditions, we select a working set, we solve the quadratic programming associated with that, and then each of these, as I went through in lecture 5, breaks into a map reduce, and the basic mapping operation in here is dense linear algebra. So if we're going to find parallelism there, we didn't find it in the iterator, we didn't find it in the pipe and filter, we have to find it in the map reduce. Okay, so let's talk about map reduce. This is the third structural pattern that we talked about in class. So recall that our definition is a little bit different from Google's. You map a computation across independent sets of data, and then you reduce it back together. So what kind of parallel algorithm strategy is that? Or what, actually, I should never say it that way. It's an artistic decision, right? Ranch house, colonial, right? Question is what kind of pattern kind of best suits it? Not always.
Is it data parallelism?
Data parallelism. Sounds about right to me. We have collections of data elements operating by a similar if not identical sequence of instructions. Sounds like a map, right? Concurrency is in the data. And moreover, here we have a stronger, what do we have in MapReduce that's even stronger than what's required here? What do we know about the data in a MapReduce? John?
They're independent.
They're independent. That's even stronger, right? This doesn't say independent, doesn't always have to be independent for data parallelism, but in the case of MapReduce, we know it's independent. So this is overqualified for data parallelism, okay? So, let's see, I guess I flashed this already. All right, so what I want to do now is briefly transition into how we then take those computations and run them on real architecture. So before I do that, maybe I should pause for a moment and ask if there's any questions. We looked at 3 types of parallelism: task parallelism, data parallelism, and pipeline parallelism. These are 3 of the colors in our palette, 3 types of architectures that we're getting used to it. We're given a design problem, what kind of architecture should we use? Is my civil, colonial, ranch house, and so forth, right? Any questions? So, Eric?
I was curious on the iterator, if you know you're likely to come out, like you're likely to do maybe thousands of iterations, if you kind of know that you're going to go through a lot of them, can you do some stuff with the prefetching that pops out of that? Is that something you think about at this level?
So, Eric's asking is, if you know you're doing thousands of iterations, can you do some sort of prefetching?
But I guess the premise is that there's no additional data once you start this thing.
Well, in each iteration loop of the iterator.
Okay.
It's a totally self-contained loop. Now, the good news about that is that you know there's no side effects. So if you find parallelism inside the loop, well, let's look at the picture as we describe this. Okay, so we're looking for, gosh, is there any way we can squeeze some parallelism out of the iterator, right? And so the good news is this is totally self-contained. So through dependency analysis, or actual the clarity in the structuring due to software architecture of this, once we know this is pipe and filter, we know, well, these 2 filters don't share any global state. So if we find parallelism in here, we know we can exploit it. If we find parallelism there, we know we can exploit it, even if there's some sequential dependency between those 2. Right. But prefetching, generally, no, that's not the first thing we look to, and yes, you were right, that's a much lower level concern. Right? I mean, so what we're going to teach you is though it's a very layered top-down process. And what you're going to discover is in all software, you're going to have a bright idea, you're going to go dive down to much lower levels of implementation, then you're going to pop back up and go, wait a minute, did I just kind of blur two filters together? And then you're going to go back and go, oh, well, gosh, this doesn't look like iterator pattern anymore. Well, actually, it's weird. And so, you know, it's not like there's something wrong with having a much lower level concern, but we are going to teach this in a kind of layered way. Okay? Any other questions?
One question.
Yeah, so.
Can task parallelism be, is there like a pattern where task parallelism pattern matches data parallelism? Like,
Oh,
through tools?
yeah. Is there a pattern where task parallelism matches data parallelism? Thank you very much. I kept trying, I think I thought of where to put it on the slide so long that I forgot to put it anywhere. Which is, so I'll pose it back to the class. All right, pose it back to you. What is the relationship between task parallelism and data parallelism?
Task parallelism is doing tasks in parallel, while data parallelism is splitting data parallel.
That sounds fine, but so using that definition, what task parallelism is parallelism among tasks, data parallelism exploits independent data, that's all correct. But using that, what would you say is the relationship between these two patterns? Which is the pipe wrench and which is the crescent wrench? Johnny? Yeah.
Data parallelism should be a form of task parallelism.
Data parallelism should be a form of task parallelism. You got it. That's exactly right. And so here's the relationship. Okay, all pipe wrenches or crescent wrenches, whenever you have data parallelism, you have to have some task that can operate in parallel on all that data. Otherwise, you don't have data parallelism, right?
So it's a subset of task parallelism?
It's a subset of task parallelism. Now, here's the general tip on patterns. You always use, or almost always, you know, every instance I can think of, you always use the most specific pattern. So whenever you have data parallelism, you want to exploit that. And if you don't find data parallelism, then you back up to task parallelism. And we'll find variations of data parallelism. Like geometric decomposition is an even more specific type of data parallelism, right? And if it's geometric decomposition, then we want to use that and not just generic data parallelism. I don't expect that to be blazingly obvious at this moment, but I'm just kind of telling you that there's, you know, don't stop with the first pattern that you match. There's only 7. Just keep trying. Eric?
Or reduction, could you think of that as kind of a blend of those two, where your reduction would be starting out with a bunch of data parallelism and then it's coming down through a sieve into just task?
Yeah, I mean, so my first point is, you know, so let's look at MapReduce. Okay, we have to have, when we map, we're mapping different, typically small, could be bigger tasks on all this independent data. And what Eric's pointing out, but then when we reduce, isn't that a kind of, particularly a kind of task parallelism? That's absolutely correct. Yeah, I mean, we can look at that. If you had looked at reduction entirely in isolation, then it'd be natural to kind of look at that. Maybe it's a head tilt. I mean, task parallelism, data parallelism, but because you're reducing things which are independent, right? So in that regard, you can say it's still a task parallelism. But in any case, when we package MapReduce all together, we definitely think of that as data parallelism. Yeah, Max.
Is all parallelism task parallelism?
Is all parallelism task parallelism? Yes. That is correct. Why didn't I say that?
Would you consider instruction level parallelism?
Oh, sorry. All parallel algorithm strategies are variations of task parallelism. Let's say that. You know, instruction level parallelism is a much lower level concern. Let's go back and look at the list. I don't.
I mean, I'm willing to assert that there's 3 dimensions of parallelism from a hardware perspective, and 2 from a software perspective.
Okay. So David says there's actually 3 types. So what are the 3 types?
Well, if I'm a machine architect, I can think about instruction level parallelism,
Oh.
data level parallelism, and thread level parallelism.
Yeah, okay, fine. David says if he thinks as an architect there's instruction level parallelism, data level parallelism, and thread level parallelism, or task level parallelism. Right?
So when you're the
That's
super programmer thinking about the machine, right?
Yeah, but we're in a very layered way going through this pattern language, right? And so we will find it useful to make these distinctions, even if we blur them later on. But in particular, instruction level parallelism is a level of concern below, we're just kind of thinking generally, chunking things up into individual tasks. And so all these, the reason all these are instances of task parallelism is, we've got to get an instruction counter going in parallel through data, or doing something, right, to have any kind of parallelism, right? So all parallelism, and the only thing which really more radically departs from which the data becomes more predominant here is data parallelism itself. Okay, maybe we can treat it as a little artistic argument or something like that. But if you start thinking in this way, I think you'll find a nice way to organize the parallelism in your code. Okay, other questions? We have time. Okay. Okay. This is from one of my recent graduates in NVIDIA research, Brian Cansaro, and this is the way he thought about parallelism. Now we're transitioning. We talked about software architecture. We're talking about how that run out on hardware. So he thinks of multi-cores, you've got a few really strong animals, like bulls or something, and then each of these oxen is like a core optimized for executing a single thread. It does really good, uses a lot of silicon area to execute one thread well. Whereas mini-core is more like a flock of chickens, and so these are trying to get some sort of aggregate throughput. And the emphasis is not here on individual performance. Now, both of these are, from an architecture standpoint, they're just different ways of chopping up how you use the silicon, right? So these are two pretty radically different approaches to how you use your silicon to get performance. Okay, so this is a little trip down memory lane for data parallelism. So these first single instruction multi-data machines back in the 80s, there's something called the connection machine, which, it's hard to imagine this. This is an era in which you got, on a good day, 10,000 transistors, 10,000, that's about 2,000 gates on a die, came up with 64,000 processors, and, but after that colossal failure, no one worked hard at this for a long time, but now that we have a lot more silicon at our disposal, this is coming back. It's called data parallelism because the source of parallelism is simultaneous operation against large sets of data rather than relatively coarse-grained multiple threads of control. Okay, so here's one picture. Here's an early article on this approach. Here's the way to think about it. Okay, so you have a single control processor with a single instruction scheme, and then you have a series of units of execution. This is a term that Tim Matson uses in his book, operating on them simultaneously. Okay, local state bits can predicate the single instruction multi-data execution. So in other words, even though I'm running the same program, depending on how things are shaping up at an individual execution unit, or unit of execution, I may decide to do that operation or not. I can't branch, do something else altogether, what the heck, run a whole other instruction stream. All I get to do is either execute that instruction or you don't. You can look at particular logic bits. You have interprocessor communication via send instruction and all connectivity is abstracted on top of this. Here's just another picture of the same thing. You have control processor, you have individual processors, network, memory. This is more of a supercomputer style of single instruction multi-bit. Okay, let's see. So let's see how this actually plays out in the kind of machines you can get your hands on. So you can have single instruction multi-data in CPUs. Okay, so your Nehalem, it has single instruction multi-data supplied to you through the SSE instructions, right? And next generation's AVX. So does the Nehalem have AVX? No, it's still SSE. Okay. Then there's single instruction multi-data as you view it when you have a CPU connected to a GPU. Okay, the CPU is like the front end, and then it issues a single instruction multi-data commands to the GPU, which acts as kind of a passive set of streaming multiprocessors. Then if we look at the SIMD strictly on the GPU, so very early back in lecture 5, I showed you some of the computation in my group would kind of go along and do some CPU execution, give control over to the GPU for a long time, right? In that case, then we're relying on this warp scheduler to issue commands to the SIMD arrays of scalar processors. Okay? So these are 3 different ways of getting single instruction multi-data in your hardware. Okay? And you will, through this course, become familiar with all those. Okay, so in summary, if you want to get maximum mileage out of a powerful piece of hardware, it's natural to kind of jump in, look at the instruction set, look at the features, do some thread programming. That's not how we suggest you do. We suggest you back all the way up to a good software architecture. We then go through this refinement down to a high performance implementation. The first important step is finding the right parallel algorithm strategy. And the good news here is there's really only 7 to worry about, right? And in some sense, they're all variations on one theme. Okay? We'll look at 3 of them today. And so next time, this is your preparation for actually beginning some data parallel programming. And David will be going about parallel programming in CUDA and OpenCL. Okay, we can cut there, David. Here's